to repeat that. Okay, so we did the first half of this in the last lesson. The words at equilibrium means we have to do the forward and the reverse reaction because that's happening at equilibrium. So on Friday, Alex, right, we did that reaction.
What?
Nothing?
Right, Alex? Yeah.
Yeah, just say yes, okay? So you have that information. So the forward reaction of magnesium ion plus fluorine ion creates magnesium fluoride. We found the concentration at that point of 0.055 for fluorine, but we said it was 0 for magnesium because all of it precipitated out, okay? So now we have to do the reaction going the other direction, which is the MgF2 breaking apart into the ions. Okay? So initially, that's our R, I, C, E. Can't get the E. I'm too close to the edge. So again, this is the solid, so we don't care about that. Nothing's going to happen there. Initially, we have 0 magnesium, but we have 0.055 here because that was what's left in the solution. Okay? So this is going to be plus X. This is going to be plus 2X. So at equilibrium, we're going to have X and 0.055 minus 2X. Not minus, plus. I'm sorry. Plus, plus, plus. That was my B. Okay, so we have the KSP value right here. So we know that KSP is going to be equal to magnesium 2 plus fluoride squared. Because that should have been a 2 there. Sorry, I forgot that. Y'all should have caught me on that. I forgot to put the 2 on the reaction because it's MgF2, and I only put 1. It's supposed to be 2. That's it. I accounted for that right there with the 2x. I just actually forgot to write the 2. Okay, so now we plug in our values, and so KSP is 6.4 times 10 to the negative 9 equals 0.055. Oh, no. Sorry. Do X first, because it's in the order. So X for magnesium, and then 0.055 plus 2X squared. This is going to be one of those examples where we have a fairly high concentration of 0.055, and we have a really small KSP value. So we're going to neglect X to make, so say neglect X. Okay? So then it becomes the 6.49, not 49, times 10 to the negative 9 equals X times 0.055 squared. So when you plug that in and solve for X, you get X is equal to 2.1 times 10 to the negative 6. So that is your concentration of magnesium. And doing a quick calculation, is that X value less than 5% of 0.055? Yes, it is. So your fluorine concentration is 0.055 molar. You'll have to watch the video. I'll explain that in the video, which I recorded. I just forgot to post. I'm going to post them as soon as we're done here. Yeah. Okay? Any questions on that? Do you understand why we had to do both reactions? A lot of people will miss over that at equilibrium and only do one of the reactions. So you have to do both because both are happening at equilibrium. Okay? All right, so let's move on to the next problem. No questions on that? Okay, sounds like we're good. Okay, then let's go on to the next problem, which is solubility and the common ion effect. Experiments show that the solubility of salt is less in the presence of a common ion. That's like what we just did earlier where we had already added some stuff. We did an equation like that. The pH can also affect your solubility. For example, if this is milk of magnesia, which y'all probably don't. That's an old-timey remedy that we used to take when we were kids for upset stomach. But basically, it's magnesium hydroxide in there. Would magnesium hydroxide, which has limited solubility, be more soluble in an acid or a base, and why?
Base, because of the OH.
Ah, but if we were putting in the presence of a base, that already contains a hydroxide, right? Mm. Yeah.
Oh, is that what you put in your stomach? Like
Yeah.
stomach acid?
So, but let's say I have this present. I'm putting this in there. If I put it in the presence of an acid or a base. Okay, so the thing that's going to react with that in an acid is the H+. The thing that would interact with that in the base is another hydroxide. Which one would make this be more soluble? It's not that like dissolved like is not a factor here. That's talking about types of bonding. Huh? I'm not even talking about a strong base. An acid, what makes an acid is a proton. It has a free proton. What makes a base is the free hydroxide. If you were trying to dissolve this magnesium hydroxide, what would this join up and make? Water. So then it would be effectively removing some of the hydroxide. According to Le Chatelier, if we remove one of the concentrations, which way does it shift? No, it shifts toward it. So that would do what to my solubility if I increase it towards that? Meaning I make more. It would make it more soluble. So it's going to be more, you'll get higher solubility in an acid because that hydrogen in the acid would react with the hydroxide and make water, effectively removing it, which means you could shift the equilibrium to form more of the ions. Okay? But if I already have an excess of hydroxide in there, am I likely to have even more dissolve? And the answer is no. Okay? Okay? This next section is going to talk about how to remove certain things in order. We're also going to be comparing and doing calculations with their KSP values to figure out which one would precipitate first. So here is just an example. Let's say I have all of these ions in solution and I want to take them out. Knowing your solubility rules, if I was to add HCl, what would I precipitate out? Silver, mercury, and lead, right? Then all of the other ones would say. So this is just taking you through the process of how you could get different ions out of solution. If I had a big mixture, it's called selective precipitation. That's what it's called. This is just giving you an idea of that. So where knowing your solubility rules comes in handy. Okay? Here are just some words of what it said it did. So you can go through that later. I want to get to the problems because you all know how to read. So here is selective precipitation. Let's say we have, now, and they wouldn't give you one with all of those in there. They're going to give you like 2 and have you compare. So this solution contains some copper and some lead ions, and it gives you the concentration. And it says if a source of iodide is gradually added to the solution, and it gives you the 2 KSP values, which would precipitate first. And then it says specify the concentration of iodide necessary to precipitate each one of the salts. Okay? Now, remember I told you last week, if you've got KSP values and they have the same number of ions, you can just look at their KSP values and say this one would precipitate first because it has the smallest KSP value. But these do not have the same number of ions. So you cannot do that. So we have to do calculations. Okay? All right. So first thing we want to do is write the KSP for each one. So we have lead 2 iodide. And then for copper 1 iodide. Okay? So and it gave us the concentration, so we know that lead is 2 to the negative 3rd molar, and copper is 1 times 10 to the negative 4. So let's figure out what PbI2 would be. So it gave us the KSP value. Times the lead value. And then we have the concentration of I squared. But remember, that would be X and 2X, right? If we were doing that based on the way it would precipitate or break apart. So when you solve for the iodide concentration, mathematically, you should get 0.001, I think, I can't read my writing because I made a mistake. I think it's 1.3. Okay? Now we're going to do, so that's how much iodine you would require? No. It's I just didn't do that. It's supposed to be equal. Yeah. So now we'll do the same thing for copper 1. So 5.3 times 10 to the negative 12 equals 1 times 10 to the negative 4 X, or iodide. So then we get iodide concentration as 5.3 times 10 to the negative 8 molar. So that's how much you would need to precipitate out the copper iodide. So which one of those is going to precipitate first? The second one, copper iodide, because we would hit that concentration right here a lot quicker than we would hit this when we started added iodide. So copper iodide, copper 1 iodide would precipitate first. Okay? Does that make sense? That's pretty straight. That one's pretty straightforward. Now, if we had same number of ions, then we can compare the KSP values, and the one with the smallest value is going to precipitate first. Yes.
So in like one you did double it because it's squared.
I did. I just didn't. I did two, when I solved for x. This was 2x in here.
So x is like 0.00.
What? I did 2x squared to get when I solved for x. Because remember when iodide breaks apart, you go, goes Pb2 plus 2 iodide. So the 2x is your value when you put in it, plug it in. I just wrote iodide, I didn't write that. Okay? And then I think that's, the rest of that is just talking about things that you can read through, complex ions and things like that. Why? Because when this breaks, hold on, let me go back. The reason it's 2 is PbI2. When it breaks apart into ions, it gives you a Pb2 plus 2 iodide. So whatever the concentration is, iodine is going to be twice as many ions, or twice as much concentration, because of that 2 right there, because of the stoichiometry of it. Okay? The last part is just things that you can read over yourself. And